Hello, everyone. Thank you for being here. So far, we put in a lot of work in preparing for this week, but this week is the actual Winogradsky column setup week. And the purpose of it is to allow us to study the soil and biogeochemical cycling. I'd like to do a little bit of a review for redox reactions. This is the most chemistry intensive portion of the course. And so I keep trying to hammer this home with us, and we'll revisit this several times throughout the semester. So it's good to be quite familiar with this. But a redox reaction is when electrons are transferred between atoms or molecules. And we saw this with sodium, Na, and fluorine or fluoride, F, when an electron is transferred from sodium to fluorine in the sodium fluoride uh, reaction. And why they're called redox reactions? Well, let's break it down into its constituent parts. It's called oxidation when a molecule or element, which is electron greedy, takes an electron from another atom. So the atom that loses its electron is said to be oxidized. The reason for this is because oxygen is very electron greedy and it tends to take a lot of electrons from different atoms. And so, usually, in fact, throughout this entire course in our organic chemistry, anytime you see oxygen with any other elements, you can pretty much bet your bottom boots that it's taking electrons or it's hogging the electrons in that molecule or in that from that other atom. And so that atom that loses an electron is oxidized. And reduction, well, we don't have a single atom that's quite as well studied like oxygen that we would name reduction after, but reduction is the other half of this interaction. So reduction would be oxygen gets reduced, where an electron is transferred to oxygen. An electron has a negative charge, and therefore oxygen's total charge is more negative. Remember, you're adding negative charges to oxygen, and the more negative charge it has, the more that charge is reduced or lowered. So we call anything that takes an electron, we say that it has been reduced, and anything that loses an electron has been oxidized. And we cannot take without something else giving. These reactions are always coupled. So an oxidation is always coupled with a reduction. And this is important because it is the transfer of electrons that allows the chemical potential energy to be released from atoms or molecules. And they do so for organisms do redox reactions for two main reasons. The first one is to assimilate matter. So a organism needs to grow, it needs to replace machinery in its cells, and it needs to reproduce, and so it needs to assimilate new matter throughout its lifespan. In addition, it needs energy. It needs to be able to store and harvest that energy. And these are the two main reasons why redox reactions occur. There were rules of thumb that we laid out, and this allows us to tell which element or molecule is being reduced or oxidized. And it's pretty simple. And it's looking at the ratio of atoms in a molecule. And the first rule is if you see the ratio of oxygen in a molecule increase from the before to the after in a chemical reaction, there's more oxygens present. That means that molecule was oxidized naturally because oxygen is a great oxidizer. Now, conversely, you could say if the oxygen ratio decreases, then we know it wouldn't be oxidation, but reduction, the opposite, losing those electron greedy atoms in that molecule. And if the ratio of hydrogen is increasing, then the molecule is being reduced. Conversely, if the ratio of hydrogen is decreasing, so the product has fewer hydrogens in it than it started with, then we'd say that it's being oxidized. So if you can remember that oxygen is related to oxidizing and hydrogen is related to reducing, you should have a pretty good understanding of when you look at any of these chemical reactions in this course, who is being oxidized and who is being reduced in any chemical reaction. And we can see that play out here with plants, algae, organisms that photosynthesize. They do it for two reasons. They want to capture solar energy, they want to capture the energy, which was one of our reasons, and they want to produce biomolecules or organic matter like glucose so that they can assimilate that matter or store it as an energy reserve for later, which we'll see in a moment. And in order to do so, they have to do a redox reaction. So if we look at CO2 and the carbon here, for every one carbon, we have two oxygens. And if we look at the product, for every one carbon, we have one oxygen. And so our ratio of oxygen didn't increase, it decreased. So we're losing that oxidation and it's becoming reduced. So we already know this is being reduced. Fortunately, we have two rules of thumb and it followed both rules of thumb, which is great. We also saw that there were no hydrogens in CO2. And now in glucose, we have two hydrogens for every one carbon. And so that means hydrogen is increasing. That also reconfirms that it's being reduced. Additionally, um, these reactions are coupled, so something has to be oxidized here. Should be quite obvious because there's only one other compound in this chemical reaction, and that's water. So even if we didn't know anything about the elements here, we know since this was reduced, the other one must have been oxidized. So let's take a look at this. We have two hydrogens for every one oxygen. And if we look at our products, now we have no hydrogens on this oxygen. And so the hydrogen went down. And since the hydrogen went down, it's not being reduced, it must have been oxidized. And so we have our redox reaction here in photosynthetic organisms. Now, I said that glucose can also store energy for later, and that's true. When we have a reduced molecule and we oxidize it, we can release that chemical energy, that's potential energy storage, and we create our kinetic energy. Now, if we look at the ratio again, we have a 1-to-1 of oxygen and a 1-to-2 of hydrogen. And we do the exact opposite of this chemical reaction here. And we can see that now we have a 1-to-2 ratio of oxygen. So oxygen went up. That means we're oxidizing, as listed here. And we can confirm it. We could stop there, but we could look at the hydrogens too and see there's one carbon to two hydrogens. That now goes away. There's no more any hydrogen. And so glucose is obviously being oxidized. There's two ways we can confirm it there. Looking at our oxygen here, we have no hydrogens, and in water we have two hydrogens to one oxygen. So the ratio of hydrogen is increasing, which confirms our reduction. We talked about the carbon cycle. Um, it's a biogeochemical cycle. It's a major element in biology. And we've hammered this home here by looking at this cycle here where both of these reactions are the inverse of each other. One is reducing CO2 into an organic molecule. One is oxidizing our organic molecule into CO2 to capture energy and release the energy. And that completes this biogeochemical, this cycle here. Although there are other ways we can process carbon, this is kind of the bread and butter of the carbon cycle. Now, we can have oxygen available at the surface of Earth, and this is the greatest way to do it because it releases the most amount of energy. The more we can oxidize something, the more energy we're going to get out of it. So organisms prefer to oxidize organic matter with oxygen and reduce that oxygen, or give the electrons to oxygen, which lowers its charge. However, this isn't the case for all of Earth. We don't have a free and abundant level of oxygen everywhere. There are many anoxic environments, maybe even more prevalent. Um, in these regions, we still need to produce energy and assimilate organic matter. So instead of reducing oxygen, we need to expect to reduce other organic matter or maybe some atoms, elements, instead of reducing oxygen. So you have to work with what you have here. And with carbon reduction, so as an organic matter, we can take organic molecules and reduce them through fermentation, anaerobic respiration, methanogenesis, which is covered in the textbook. Nitrogen reduction is another common one. So we might denitrify, we can take nitrate. See how the oxygen's loaded on here? Obviously, this is a very oxidized compound, and we reduce it, lowering the oxygen ratio to gaseous molecular oxygen or dinitrogen. You can call it any of the above. Sulfur reduction is the one we are going to really analyze in our Winogradsky columns. So here we have this highly oxidized sulfur, sulfate is what it's called, and we can reduce it by turning it into H2S or just elemental plain old sulfur. All right, so here's our basic chemical equation again for aerobic cellular respiration. And like I said, we need to reduce something else instead of oxygen in an anaerobic environment. And so in our Winogradsky columns, we're going to replace it with a lot of sulfur compounds, namely sulfate, could be sulfur as well. And that's going to be the compound that's reduced. Sulfur is a very common mineral found naturally in rocks. These are mineral deposits, and it gets into the cycle through weathering and erosion. And then in soil or water, it can then there be converted into sulfate, SO4. Another form is sulfur dioxide, which is emitted through volcanic eruptions or the burning of fossil fuels. So here's our biogeochemical cycling. We can see that it interfaces with abiotic and biotic components here in Earth's systems. And we're going to be really focusing on up through the middle here. So when we have sulfate, remember it turns into sulfate in soil or water. Um, and you have conditions that are anaerobic, you can have bacterial reduction in order to turn it into reduced sulfur, H2S and HS, or hydrogen sulfide. And when oxygen is present, well, just like we saw the cycle in photosynthetic organisms and organisms that do cellular respiration, these different bacteria can oxidize it. So they can oxidize it as well. So we can go in both directions here. Okay. And the two most common microbial culturing techniques used in labs is a liquid culture, are grown on top of a petri dish, and these mimic more aerobic environments, and they're very homogeneous. Everything gets to have oxygen exposure here, and so you can easily cultivate one organism. This is on a shaker, and it mixes everything up really well. So the environment is basically the same at the surface or the bottom. We are going to make our own Winogradsky columns. It's not going to be quite as fancy as the one seen here, but it will get the job done. This Winogradsky column at the display in the Harvard Museum of Natural History is an ongoing display that shows the same sort of reactions that we're going to be taking a look at. And in the environment, most things exist in what we call microbial mats. And so, as we showed with oxygen being present or not present, can determine what sort of microbes grow in the sulfur cycle. That's what we find in the environment. We see different layers where there's different chemicals, and different availabilities of oxygen. And then we get different organisms that can live in that particular environmental niche and take advantage of those conditions because they are tuned and involved to survive there. And here's another example in Yellowstone of such a microbial mat. We previously discussed that there are three zones based on oxygen availability. We have at the top, we have the oxic zone. So this is where there's a free and abundant level of oxygen. In the middle, we have the suboxic zone. So this is where oxygen is beginning to be depleted and it's not as free and abundant in the oxic zone. And then anoxic, an means without. So this is where there's basically, for all intents and purposes, no oxygen available. And the availability of oxygen, because oxygen, again, is so desirable for efficiency in making energy, you can see that it's really going to determine what sort of chemical reactions organisms can do to make a living. So let's take a look at this. At the top two layers here, particularly the very top of the oxic zone, you're going to have your photoautotrophs. And these photoautotrophs um, have access to sunlight at the top. And on this column here, we can see the chemical reactions that take place. And so photoautotrophs, they take water and they turn it into oxygen, and they take CO2 and they convert it into glucose. Here, glucose is abbreviated. Instead of saying 6 carbons, 12 hydrogens, and 6 oxygens, we just divide it by 6. So it's 1 carbon for every 2 hydrogens, and then there's 1 oxygen for every 1 carbon. CH2O is just a shorthand for glucose because glucose is a carbohydrate. It's a hydrated, or it's a water with a carbon molecule. And so we can see the arrows, they start with a reactants, CO2 and water, and they show you what you end up with, oxygen and glucose. Let's work our way all the way to the bottom here. At the bottom, oxygen is not available. And so you have these sulfate reducing bacteria that are going to make hydrogen sulfide through the reduction of sulfate. Let's see what that looks like here. So we have our sulfate and it's replacing our oxygen. And we're going to oxidize sulfate, we're going to reduce it into hydrogen sulfide, and that allows us to generate energy. And again, we're taking, just like we saw with cellular respiration, we're still taking our glucose, our carbohydrate, and fully oxidizing it into CO2. So these electrons from sulfate um, are used here for the reduction into H2S, and the electrons are handed off from glucose to sulfur in this process. So we can see the ratio of oxygens going up, and so it's being oxidized, and the ratio of hydrogen is going down, which also tells us it's being oxidized. So we've oxidized our glucose and we've reduced our sulfate, just like we see with cellular respiration, only sulfate replaces oxygen. We work our way up here and we can see that these are called chemoautotrophs because they're not using organic matter for their processes. These ones are green sulfur bacteria, and they can reduce carbon in order to make biomolecules. So they've made their glucose, so they can make their own glucose. In order to do this, though, we can see that they need to oxidize this hydrogen sulfide that's produced by the sulfate reducing bacteria. So we can see the cycle taking place. This waste product can be used here in order to generate biomolecules for green sulfur bacteria. These two layers above, now we're going to start going the other way. more oxygen is present. And so these organisms are going to start oxidizing these reduced sulfur compounds. So they will reduce hydrogen sulfide and sulfur into sulfide and then oxidize it and then fully oxidize it into sulfate. And in doing so, they can make glucose. And here is the chemical gradient then. We can see hydrogen sulfide is going to be highest at the very bottom, where lots of reduction of sulfate takes place. And then sulfide is going to be very low at the top, where lots of oxidation of sulfide into sulfate is going to take place. Here is another Winogradsky column with these different bacteria pointed out. So we have our green sulfur bacteria, our purple sulfur bacteria, and we have a purple and green non-sulfur bacteria. Here's the anaerobic zone, here's the aerobic zone, and then cyanobacteria are a photosynthetic organism there at the top. Again, we have these sulfate reducing bacteria that make H2S. And many of you may have very clay-like soils. And if you have a lot of clay in your soil, you might have a lot of iron present in the soil. And this iron will react. And so the sulfite can react with iron and it forms iron sulfite here, or pyrite. And this might appear as black spots. This particular Winogradsky column, they added iron, so they did kind of cheat. But what you'll see is probably black splotches that occur over time in your column. Let's go over the materials now. So now let's go over the required materials for this lab. First and foremost, you're going to need a transparent 1 liter bottle. You're going to need 5 of them. I recommend plastic bottles here, and be sure you get a 1 liter bottle. Do not get a half a liter bottle or a half a quart. It needs to say 1 liter, 1,000 milliliters, or maybe it says very close to that, like 950 milliliters or something. Very close to a 1 quart, a 1 liter, or 32-ounce plastic bottle. You will need 5 of them. If you do not have a funnel at home that from your kitchen or somewhere that will fit inside of the mouth opening of the bottle, you're going to need a 6th bottle. And that's to create a funnel out of it, which you'll be able to see in your setup column section on how to make a funnel from a bottle. Other components you're going to need. And also, I originally had certain parts of these highlighted in red for what you needed, and black we would have in the lab. This is an online course, so you have to provide all of these materials. But to go get you're going to go acquire a soil sample from the field. And so you're going to need all of these materials for that. You're going to need a shovel or some sort of a trowel for digging up the sediment sample. You will need a permanent marker for labeling your columns. You're going to need tape to create labels for each bottle. And then you'll write with the marker on what sample you have, how you've set it up for each bottle. There'll be different ways that you mix ingredients for each of the 1 liter bottles. You'll need water. I prefer if you have like a big, maybe a gallon milk jug or something to carry a bunch of water from the source. That works best. But if it's too much of a hassle and you don't have a proper lid for it or something for a bucket and you're afraid of it sloshing around, or you have to take public transit, don't worry about that. You can use tap water and the experiment should work just fine. And in order to carry your soil home, you're going to need a large container. So a 5-gallon bucket is awesome, but something that's going to hold at least a gallon or 16 cups of soil. And lastly, you're going to need a digital camera or a cell phone camera to take pictures of the site that you acquired the sample. It's going to be required for your lab report this week and your final submission of your lab report. Additionally, back at home, you're going to need some things. You're going to need you're going to have to find a location. This could, it needs an area for you to put your water bottles or your Winogradsky columns in a brightly lit windowsill. So it has to maybe be a sun facing windowsill, or just put it outside in direct sunlight. If you have a little place that you can section off outside and the bottles aren't going to be harmed or knocked over throughout the semester. And so they need to be able to sit undisturbed for a solid 8 weeks, at least. Next, you're going to need a measuring cup. You're going to have to measure 1 cup at a time of the sediment and have additives as well added. And to some of the Winogradsky columns, you're going to add a carbon source. This carbon source is going to be shredded newspaper or notebook paper. And what you're going to do is shred it up into fine little pieces of paper. And you're going to need about 2 loosely packed worth of this paper. So when I say loosely packed, if you think about, if you took a textbook and you were to cut a hole in it, they're laid perfectly flat, one on top of the other. But if you were to loosen them all up from each other and shred them up into little pieces, they'd be much more fluffy, and that would take up a bigger volume of space. So loosely packed, roughly 2 cups of shredded newspaper or other sort of notebook paper. When you take your sediment sample from the field, you're going to want to get about 16 to 18 cups of sediment, no less than 16 cups. So make sure you're at 16. Taking a little bit extra is fine. You can always get rid of it if you don't use it. You'll also need 4 eggs, liquid dish soap. And so this is soap that you would use to clean dishes in your sink. We're not talking about liquid soap that you might use for doing the laundry or powdered dish soap. A ruler for doing the soil texture analysis later on. And like I said, a funnel that where it fits inside of the mouth of your bottles would be great. I would also recommend, if you have a spray bottle, to use a spray bottle. There's a tip to getting around it, but the spray bottle will, after you put in all of the soil and mix it up with water, it's really gross on the inside, and all of the inner wall is covered in dirt, and so you can't see what's really going on. So you can use a spray bottle to spray off the inner side walls and spray down all of the soil, so it's all at the very bottom of your bottle and not all over the place. Okay, let's talk about collecting the sediment sample. The best samples, the best resources to get your sediment are going to be a stream, creek, marsh, pond, bay, ocean, it, or even a backyard puddle, somewhere that's wet if you can. If it's dry, that's okay. It'll probably work, but it would be best if you get something that that is wet all the time or wet occasionally. I had a student that got a sample from the Salt River last semester, and it was wonderful. I'll just make a note here that if you choose a soil that has a lot of clay, it's fine. It's going to work. But when you pack it away, it's going to get really compacted and stuck together. And when you do the following subsequent steps, where you have to mix in the eggs and the newspaper and the water, you need to be careful to thoroughly break up that clay so that it can mix up well with the newspaper, eggs, and water. So imagine if you're making bread or a cake, you don't want any clumps of flour in that bread or cake. And the same is true with mixing up your soil. So you're going to have to take extra time. I can't give you an exact amount, as long as it takes to get the job done. So you're going to get your sediment collection container, could be a plastic bucket or whatever, with a lid if available, a shovel or trowel, and your camera. You're going to go out, get that at least 16 cups of sample from a preferably wet or moist area from your sample site. And then this is important, pick out, as you're collecting it, it's easier to do it there on site. Pick out any obvious major rocks, that are bigger than, say, a dime in size, or any other major debris. So sticks, things like that. You don't want that getting into your Winogradsky column, and it's going to make it hard to get into your bottle. And so we want to get rid of anything basically about an inch in diameter or larger, or about this, or even smaller, maybe a dime in size and or larger. Next, before you leave, make sure you take photos of the sample site to add to your lab report. We want to see where you got the sample from. And then you will return back to home to assemble your Winogradsky column this week. So if you do not, so what you see in this image right here is the setting up of a Winogradsky column. This is the control column. We're trying to get the soil in it first. Now, I did not have a funnel, so I had to make one out of that 6 water bottle I told you. So you can take that water bottle, you cut it in half, turn it upside down, and tape it to the lid of your other column. And then that allows you to scoop up a cup full and dump it in there and shake it in there, poke it in there with a butter knife or a stick, chopstick or something, whatever you need to do to get it down in there. And you're going to take your 5 other water bottles. You got to get the water out of them first, and then place that piece of tape along the bottom and label each bottle either a control, texture column, carbon column, sulfur column, or carbon plus sulfur column. I would recommend wearing gloves when you're at step 3. So this is you've made your funnel. Step 3, you're ready now to break up your sediment in your soil so that you can get it into your different bottles and mix it. I'd recommend a pair of gloves if you have it. If not, that's okay. Just wash your hands when you're done. You're going to get dirty here, and you're going to break up any large clumps of dirt. Remove any other debris that you missed that's not going to fit through the mouth of the column. And so this will make it a lot easier to do it up front, especially if you have very clay-like soil, because once it's in the bottle, it's really hard to shake and disperse it. So spend a lot of time here on step 3 to break it apart. All right. So that is that. The instructions will have more details in the actual lab protocol posted under this week's learning module. Let's talk a little bit about, we've talked about biogeochemical cycling. We're also going to look at our soil texture. And you're going to have 5 bottles. One's a control, one's a carbon, one's a sulfur, one's a carbon plus sulfur. That's 4. And then there's the 5th bottle you're going to make called the texture bottle. And this is something totally separate than those other 4 bottles. This is something that can be done in a week, and when you're done with it, you can throw the texture bottle away, and it's going to be treated a little bit differently, and we'll talk about that. And it's going to be used to analyze the soil texture of your sample. And we've discussed this a couple of times, where there's 3 different components to the solid phase of any soil. There is the sand component, the silt component, and the clay component, and they're differentiated by the size of the particles. Sand is the largest size. We say 50 to 2,000 micrometers. What does that mean? Um, well, it's about the size of sand at the beach. Then we have silt particles. This range is the mid range, 2 to 50 micrometers. This size is about the size of, if you've ever made espresso coffee, finely ground coffee, or if you've ever, if you ever pour out some black pepper, you can look at the little teeny little flakes there. It's about that fine. So you can still see the individual particles. And then we have clay, which is the smallest particles. This is down to the molecular level. You cannot see the individual clay particles. In the image here, yes, you think you can see little clumps here, but it's just because the clay is kind of sticking together. But you're not going to see individual colorations of particles like you might see with silt. I'll show a picture of that in just a moment. Sand is really good drainage. These big particles allow water to easily go through the soil, and it's very clumpy. Really think of sand at the beach. Silt is in between. It has moderate retention, so the water can't slip through quite as easily as the silt. And again, think fine coffee grounds or ground black pepper. And then clay is very poor drainage, so the water in this sort of soil really gets waterlogged and trapped in the soil and doesn't easily flow through it. And when it is wet, it's more like a paste. So you're going to observe a paste-like layer in your soil. We can use these three to determine the soil texture. We've gone over this a couple of times, but basically you measure the different proportions. So you're going to have your soil texture Winogradsky column, and you're going to mark with a Sharpie these different layers here. And as you can see, you can see big clumps here, kind of like you might see at the beach. And at the very top of that, you're going to mark with a marker. And the silt one, again, is like ground pepper. And so you're going to see little dots of different colors, a black spot here, a brown spot there, a white spot here, just teeny little pieces like pepper flakes. And you're going to mark the top layer of that. You can tell the difference between silt and clay. See, clay right here looks like this fine paste. And if you were to run your fingers through it, it would feel like paste as well. You have to let your soil texture column, after you set it up, settle down for a while. The soil is going to compact over time. And also all of this is clay in suspension, and it'll take time for that clay to settle out before this clarifies. And so this clay layer will be even bigger. And you can take a ruler and measure the total length. This will come next week too, so you don't have to get all of this information down perfectly. You can review this and your protocol when the soil texture lab comes up, but you'll measure the total height, and then the height of each one of these, the thickness of each one of these over that total height will give you the percentage. So it's 60% clay, 30% silt, and 60% sand, and then 10% clay. And you'll take your soil triangle, you'll mark these lines, and then you'll draw where they intersect, and that tells you what sort of soil you have. So this is a sandy loam soil. All right. And so I've taken an excerpt here about adding water to your column. So after you get the soil in there, you're adding water. I say add 1/4 cup at a time and pause. Mix and shake really well. So put the cap back on and give it a really good shaking. You want to add 1/4 cup at a time because you can put water in, you can't take the water back out after you've added it. So add it very slowly. Take your time at this step and keep repeating until the mixture has a consistency of a thick milkshake or an ice cold slushy. So it's so thick that when you turn it upside down, it just barely kind of runs down with gravity there. It's quite mushy, but it's not It's not soupy at all or runny at all. And this is different than the texture column. The texture column gets treated differently. In order for you to get all of these particles broken up from each other, so there's no longer any clumps, they're broken down to the individual pieces of sand and silt and clay, we need to add a little bit more water than the other columns. So you want to add another 1/2 cup roughly. You want the consistency of a melted milkshake, so it's pretty runny when you turn it up and when you invert the bottle upside down. And you want to shake this one up really well to break up all the particles. And then we need to help break it up even more. And we can add a surfactant, or we can add liquid dish soap. You want to add about 1/8 of a teaspoon or about 3 drops. If you add too much, then it gets too foamy to mix it up. Put the lid on and shake vigorously. You can let it rest, come back and shake it vigorously again. Maybe let it rest till the next day, come back, shake it up again. You want to allow that dish soap to get in there and coat those surfaces of those soil particles and break it up a lot better so that when the bottle is left to settle, the sand is all separated from the silt and the silt's all separated from the clay. So the sand settles almost immediately, within a few seconds. And the silt will settle pretty quickly as well. And then the clay can slowly come out of solution over time. So do this week. You're going to need to post your week 0 documentation. You're going to look at the lab protocol and read the record Winogradsky observations portion of the protocol. Make sure steps 1 through 4 are all done. You're going to make sure you include a picture of your sample site and all of the columns are set up, and you're going to take a picture of all of your columns, clearly take a picture, and you're going to write a caption underneath those columns to describe their appearance, and you're going to submit that as documentation or proof that you got your Winogradsky set up here on week 0. Now, additionally, you've mixed up your soil. Like I said, the texture column is something different we're going to do the next week, but you've made your soil texture column this week nonetheless with your other Winogradsky columns. You're going to let that soil, the clay, take some time to settle, and it's going to compact. So you're going to give it about 5 to 7 days, and then take a Sharpie or a marker and mark those different levels. And that's what you're going to use for your soil texture lab the following week. So we want to make sure we mark our layers before too long, because if there starts to be microbial growth in there, it might be hard to read those different layers. Follow the descriptions on the previous slides for how I described to tell the difference between those different layers, and do your best job possible. It might not be perfect. Maybe you're not going to find the exact moment where sand becomes silt. It's a gradient there. But follow those directions where you're looking for big clumps, and then the silt is just very small little speckles like black pepper, as I described. Then you can set that texture bottle aside and use it for your texture lab when we do that the next week. If you have any questions about any of the setup, please do not hesitate to reach out to me and ask. I know there's a lot of steps here. I tried to make clear directions, but I'm here to help. If you want to schedule a virtual appointment too, we can look at your bottles together, and that might be a little bit better. But please reach out to me, and thank you so much for watching the video, and good luck everyone on your Winogradsky.